Okay, so this is another take of the lecture on beats. You already know that when you have two vibrations, um, they beat together and create beats in time. So, for instance, when we had long ago, an example was uh, that you had a harmonic system, and you had basically producing uh, two different amplitude. So A was, say, cosine omega 1t, and you had x2 equals, for simplicity, was, say, A cosine omega 2t, um, omega 2t. So, this can happen, for instance, if you have two mode system, and you had particles going at different frequencies. Then what is the resulting movement occurs. So we had said, if I add these guys up, uh, it gives me 2a cosine omega 1 minus omega 2 over 2t, and cosine omega 1 plus omega 2 over 2t. And we said this part was a slowly varying function, and this part was fast. So this is the slow function, and this was the fast. And the result was, so if I plotted this x versus t, you got something like, it's kind of slow one acted like an envelope within which the fast one was being fit. So the net result was just so this is coming from before. So this was vibration. It's not a wave. Now we're gonna look at say, now we want to look at a wave picture of this. We have a vibrator which can vibrate, to attach a string to it, and maybe this string is very long, but somewhere there, way out there, is tight, so that tension is T and its mass potential mu. Now when I vibrate at one frequency, say this one, this will send a wave of frequency omega 1, right? So it will create a harmonic wave of frequency omega 1. So omega 1, and this will move this way, right? Now if I were to do this with at a slightly higher frequency, what will we get? We will get a maybe same amplitude, okay, but at higher frequency it will look like this. but it's going to still be cosine. Oh, it still be cosine. So so you have that. Now if you do it at that, a combination of them, so basically this is the way my oscillator will oscillate. This oscillator will over here is going to oscillate in this manner where it has beats and such. So it will produce waves which the question is what kind of waves it's going to produce, you know. So if I oscillate this, oscillate at a in a BT fashion, right? So if I oscillate using this kind of, well, if this is oscillating up and down in this manner, what kind of wave it results in there? Well, to answer this directly, we say, well, this is nothing but harmonic waves, and we know each of the harmonic waves is going to create its own. So this vibration of the generator will create a wave psi1 of x, and this wave, that the blue wave psi1 of xt, that's going to have some amplitude a, and it's going to be cosine k1x minus omega 1t, right? So k1 is going to be 2 pi over lambda 1, and omega 1 over k1 will be the v1, and is velocity of this wave, and then this would also be, because of a string, it's going to t over mu. Okay, let's see if I do the red wave. So the red one, this will generate a wave which will be psi2 of xt, and that's going to be a cosine. I'm just going to, for simplicity, I'm going to say it's the same a k2x minus omega 1t, and k2 will be 2 pi over lambda 1. In the example given, lambda 2 is smaller, this lambda 2, so k2 bigger, lambda 2 is smaller, and omega 2 over k2 will be the velocity for the red wave. So that will be equal to square root of same t over mu, right? So here we have our same v1 equals to v2. That's a special case. The net, which will correspond to the wave generated by this kind of motion, so the psi will just be equal to psi1 plus psi2. So this thing, adding two waves, is called superposition of waves. And it says that if you have wave 1 and wave 2, the net wave is just by adding the two. And this claim, so you have a claim which may or may not be true, right? So the claim is if in some region of the space, which is happen to be string here, space, you have two waves, psi 1 and psi 2. It doesn't say what kind of waves, so it applies to a whole bunch of waves. Um, for instance, two sound waves, and the region can be maybe you at your eardrum, for instance. So two sound waves come at your ear. How would the ear vibrate then? You know, so that it says that psi 1, psi 2. Then the net will be the psi will be psi 1 plus psi 2. So this is a claim, and you have to make verify whether the wave you're working with obeys this claim. And this claim comes from linearity of our equations. Well, let me say name of this. This is called the superposition principle. Very powerful. You can see why it's very powerful. You can study very simple things like cosine waves, harmonic waves, and add them up to get a pretty complicated waves. All right, so the question is, when I add these guys over here, what will be the case? Well, the math that happened over here, right? Math that happened over here, it was just basically using cosine A plus B formula, right? It was using this equals to 2 times cosine A minus B over 2, and then cosine A plus B over 2. Using that math, it still applies, and so we have 2A. We have 2A cosine K1 minus K2 x, minus omega 1 minus omega 2 over 2t, and these are grouped together because these guys are constants, and this is it's a slowly varying function. For instance, omega 1 to omega 2, this all cancel out, right? So it become constant. So to the degree that omega and omega 2 are different and k1, k2 are different, they're slowly varying functions of x and t. So it times the fast one is cosine k1 plus k2 over 2x minus omega 1 minus omega 2, omega 1 plus omega 2 over 2t. And when we had this, this part is called modulated amplitude. Why? Because A is the amplitude of each of the waves. And why is modulated? Because this whole thing here is almost constant over a period of this guy. This you can take an example, work out an example for, say, k1, maybe omega 1 equals to 10, 20, and omega 2 equals to 9, 80, k1 equals to maybe 20, 40, and omega 2 equals to 1960. So work this out what it looks like. You will find that this thing that I have boxed in, this part does not change during one cycle of this thing. So let me plot this. It's going to look like this. So if I plot this guy, this just is just a very fast varying cosine. So it's just going to be between +1 and -1 cosine, right? So say this x and some t equal to 0, I plot this, okay? So t equal to 0, so I'm just plotting like this part as a function of x. So if I look at it, if I look at this part, well, let's pick another ink for it. So look at this. I've gone through the one whole cycle, and there's hardly any change in this part, this cosine part. You look at another cycle, hardly any change. Another cycle, hardly any change in from this to this, and you've gone through the full cycle of the other thing. So you can say this is almost constant as far as this guy is concerned, right? So net result actually is very interesting. Net result is if I put them together, the net result is going to be between plus 2a and minus 2a. So this will be plus 2a and this will be minus 2a, like this. When these guys are both in agreement, and +1 at some point is going to be over here, and say at some point they both agree, both of them agree. So the other guy was going to, the slow guy is going to go, like that. So, right, slow guy is going to be a cosine like that. If I just 2a times that, and he said 2a times this this other guy will be, believe it or not, is going to be this slow guy will act like an envelope within which the other guy is going, okay? So the net effect will be so the net effect the net effect will be so you can start out anywhere, and so the net wave will look like this, and the frequency of the fast one. So it's kind of hard to draw. You get you get the idea of what's happening. So this phenomena, so this is what drawn is the net. Okay, that's you might say I've drawn this guy in blue here. Okay, so this is at some time I've drawn, say I've drawn this as you can say I've drawn this as some time t, and then this whole thing will be actually moving to the right, because the signs of these these two are opposite, so the wave is moving to the right. Okay, so it looks almost like same thing as a beat phenomena, except that these are waves, and when we are looking at earlier, the vibration, uh, this guy was not going anywhere. So that thing is a vibration of this thing does not have moving in terms of place to place. It was your oscillator, the tip of the oscillator was going up and down in this pattern. So it was just at one place. And here I have a situation where what that is caused is made a wave to be generated, which looks like similar pattern, but it's a wave that travels from place to place. So if I drew the same thing at a little bit later time, so it's going to be a little bit later time, it would be like at this place. So you can it's hard to kind of sort. You can see the textbook. Chapter 6, and you can see pictures were drawn on page 294. So say what will happen, suppose this wave was coming and this was a sound wave. An example, say this was a sound wave, and this is where your ear is. Okay, so this wave will enter. Well, you are going to, when this part comes in, you're going to see the loudest, and this part is softest, and this the loudest turns into softest, and then softest. So you can see that from loudest to loudest time is called beat period. Well, beat period, if you look at this envelope part is from here to here is one period. This is one period for this wave, right? So one period, this is the one period of, so this is beat period is half period of this part. So this will be equal to, so what's the period of this part? It's in the time part. So half of that will be, if that was omega, it's going to be 2 pi over omega, right? So 2 pi over omega 1 minus omega 2 over 2. Let's make it absolute value, just make, because the period is a positive number. So you see the beat frequency is just the difference. So beat frequency is just going to be omega 1 minus omega 2. This angular frequency, and beat frequency is just f1 minus f2. Let's another aspect of this would be, I think we can stop at this point. So next what we're going to do is try to figure out what happens when we add what happens when we add many waves of, say, n frequencies. And to do the simple one, I'm going to do, say, I have omega and omega plus epsilon, just all of them just tiny bit different from 2 epsilon, so the math is easy to work out. And then omega plus n minus 1 epsilon, right? So we have these waves of these frequencies, and they're being generated from a generator which is vibrating with all of these frequencies at the same time, with same amplitude. And the question is, the wave that's gonna, what kind of crazy thing would happen? We will try to figure out what will happen there, right? So not only we're learning how to think about these things, but also see that they do follow from our math of classical wave equation. So that's one of the other things we're learning. Not just we're learning how to think about physically what's going on and what to expect, but also mathematically can we see those things emerge when we study the classical wave equation. I'm going to stop here and see if this video worked out nice. It's take 2, and I'm not sure about the new system working with